Imagine a brand new carbide insert, worth thousands of rupees, shattering into pieces inside your CNC machine. You check your G-code. It's perfect. You check your material. It's correct. You check your coolant. It's flowing. So what went wrong? The answer didn't happen in your code or your machine settings. It happened in a microscopic fraction of a second, right at the cutting edge. When you watch a CNC machine running at normal speed, you just see sparks, coolant, and a blur of metal. But if you slow that camera down to 10,000 frames per second, a terrifyingly beautiful world appears. A tool approaches solid steel. There's no sound at first, just pure, crushing tension. Then, contact. Under extreme pressure, the metal doesn't just cut like wood, it behaves like a thick, glowing, resistant liquid. That tiny split second is called chip formation. And here is the brutal truth that separates amateur operators from master machinists. Most people focus entirely on the machine, the horsepower, or the parameters. But the entire success of your component depends on that invisible moment where solid metal transforms into a chip. If that fraction of a second goes wrong, your surface finish is ruined, your tool dies, and your profit disappears. The misunderstood report card. Think about the last time you cleaned out your machine's chip conveyor. You probably saw a massive pile of different shapes, long, bird-nest spirals tangled around your tool holder. Tiny, sharp fragments flying off during a heavy phase milling pass. Deep, blue-hot curls dropping from a heavy turning operation. Or a fine, powder-like dust gathering at the bottom of the enclosure. Most people look at that pile and think one thing, that's just waste material. Let's pause right there and change your entire mindset. What you are looking at is not waste. You are looking at a physical report card of your entire machining process. Every single chip falling into that bin is trying to talk to you. It is a permanent record of the exact stress, temperature, and friction that occurred inside your workpiece. The chip is not the byproduct of machining, the chip is the ultimate truth of your setup. If you know how to read them, you can look into a scrap bin and instantly tell if the operator ran the feed rate too low, if the insert geometry was wrong, or if the tool was rubbing instead of cutting. Metal flows like liquid. To understand this language, we have to zoom directly into the shear zone at a microscopic scale. When a turning or milling tool hits steel, it doesn't slice it like a knife cutting paper. A knife separates material by wedging it apart. A CNC tool works through extreme compression and plastic deformation. As the rake face of your tool pushes forward, it forces the metal grains to compress until they hit their breaking point. This area is called the primary shear zone. Under hundreds of tons of localized pressure, the microscopic crystalline structure of the metal actually deforms, stretches, and slides along internal shear planes. In slow motion, it looks like a wave of solid metal turning into a thick fluid, ribboning upward and away from the workpiece. As that ribbon slides up the face of your tool, it encounters a second obstacle, friction. This creates the secondary shear zone, generating massive thermal energy. The chip you see flying out isn't just a piece of metal. It is a compressed, highly stressed, heat-absorbing crystal structure that just underwent an intense physical transformation in milliseconds. If you are machining a hard or brittle material like cast iron, the metal cannot deform plastically. Instead, it undergoes brittle fracture. The material shatters into tiny, discontinuous powder fragments. If you see this happening to regular steel, it's a warning sign that your material is work hardening or your tool is violently rubbing instead of shearing. 4. The micro-welded edge, built-up edge. If your chip formation looks irregular and rough, the heat and pressure might be causing the chip material to literally weld itself onto the nose of your tool. This is called a built-up edge, BUE. Fragments of this welded metal periodically break off, tearing chunks out of your tool coating and leaving a horrible, rough surface finish on your final part.